Any other logistics questions before we start the lecture? Okay, so today we are going to finish finite difference and start finite volume. The part we are going to finish, the only part we left in finite difference, is actually not exactly about finite difference itself, but generally about a discretization method for solving PDEs. And it is on error equations or error analysis, not only for steady state PDEs, but also for unsteady PDEs. So remember, we did an error analysis for steady state PDEs for Poisson's equation, right? We concluded that if we have a second order accurate scheme, that means the truncation error. So let's review truncation error. Truncation error is defined as the difference between our analytical derivative minus our finite difference approximation, let's say A times U, right? So the difference between the real differential operator and our discrete numerical approximation, that's truncation error. We also have the concept of stability. Okay, let's define this as tau. The stability means the ratio between the norm of the error and the ratio and to the norm of the truncation error is bounded. It's bounded by some, let's say, bound that's independent of grid size. All right, so that means if our truncation error decreases as our grid becomes bigger and bigger, or grid spacing becomes smaller and smaller, and the ratio of the error to truncation error, I mean, this error is defined as U numerical minus U analytical, let's say U exact, right? Then we know that as we decrease the grid spacing, our numerical solution would converge to the exact solution. That is what we want. And today we are going to look at how can we do this for unsteady PDEs. And we are going to see that it is a little bit more complicated unsteady PDEs because the error would accumulate, would be carried over in time and accumulate for unsteady PDE. So it is not just like a one norm, one like ratio of the norms. The truncation error actually get carried over to the solution error, accumulated over time and evolve over time. So stability becomes more of an issue, more important, and more of something to consider. Sometimes you may want a less accurate scheme but having better stability properties, so that like each time you are getting more error, but the error doesn't accumulate that much. Okay, so let's look at what the error equation is. Okay, so for unsteady PDE, for example, let's consider the simple advection equation: partial U partial T plus let's just say partial U partial X equal to 0. So this is an analytical PDE. All right. Okay, so we discretize it into something I'm going to write in a very generic way. Okay, a U of n plus 1 equal to an evolution matrix. Let's just say M times U of n. M is a matrix that carries the solution at step n to the solution at step n plus 1. All right. Okay, so now if you look at the solution error, so this is the numerical solution. Again, the hat, let's say the hat is numerical solution, and without the hat is the analytical solution. So I don't have to write numerical and exact all the time. So if we do that, if we do that, then as we plug in the analytical solution into the numerical operator, this is no longer satisfied, right? This is satisfied only up to a truncation error, tau of n. Okay, and this tau of n contains truncation error both from the time discretization and spatial discretization, right? Contains tau from time and space discretization. Now, when you subtract these two equations, and if you define En to be Un minus U hat of n, then what we have is En plus 1 is equal to the same m times En plus tau of n. So we get an evolution equation for the solution error. Okay, every time we advance to the next time step, the previous solution error is carried over, multiplied by the evolution matrix M, and M is the discrete evolution matrix, and then added up with the truncation error introduced in the current time step. Okay, so the solution error at time step n is really like an accumulation of the solution error. So if I can write it down, write this, if I can expand En again as m times En minus 1 plus tau of n minus 1 plus tau n, and etc., we can see that like it's an addition of n terms. Basically it's n terms added up, and the earlier terms gets multiplied by the matrix M for more times. And that brings some skills we learned from the iterative methods, that as we multiply a matrix for n times, what determines if m to the n times e is becoming bigger and bigger as you multiply m more times, or become smaller and smaller? The eigenvalues, right? So stability in this case has a lot to do with the eigenvalue of the matrix M. We want the eigenvalues of the matrix M to have to be bounded between minus and 1 and 1. If the matrix M, which is a discretization of the time evolution, has eigenvalues that goes beyond the unit circle in the complex plane, then we are in trouble. Because no matter how accurate your discretization is, you can use a very, very accurate discretization, and the error, no matter how small it is, just accumulates, not only accumulates, but grows, right? Like if you have a paper that is like 1/100th of an inch thick, you fold it by 50 times, how thick it is? Any idea? Huh? Yeah. Yeah, it's about the distance, the thickness from the Earth to the Sun. So that's how problematic it is if you have an M that with the eigenvalue of, let's say, -2, right? If you're not careful, you may get an eigenvalue of M that is like -2. Well, may not be a big issue, but like if you apply this, evolve it for 50 times, you get numbers that are ridiculous. And if you evolve it for like 500 times, you get nangs or infinities, because like computers no longer can represent that big numbers. Okay. Cool. So that's the effect of stability in an unsteady PDE. But how do we? Yeah. Question? To what? Yes. Yes, it is similar to unsteady problem, except for like in iterative method, we are just solving the linear system. So we don't exactly have the difference between an analytical operator and a numerical operator. So the tau doesn't come up, right? So in iterative methods, we just have an initial solution error, and that just gets multiplied. And in this case, we don't have an initial error. We just have an error that gets compounded every time step. Each time the error is small, but like the accumulative effect may be big if your M has eigenvalues greater than 1 or exactly equal to 1. It is also not good if the eigenvalue of matrix M is exactly has a norm has an absolute value exactly equal to 1. That way, the error accumulates linearly. It doesn't grow exponentially, but like it's also not a good thing if the error accumulates linearly. All right. Okay, now let's discuss how do we find the eigenvalues of the matrix M. Of course, you can do a matrix stability analysis like we did in the steady state case. That requires you to have the full matrix M. And that's the right way to do it if M has complicated boundary conditions, for example. And you want to make sure your boundary condition discretization is okay. So, I mean, a lot of the stability problem can be caused by boundary conditions, as you may have learned in Project 1. But in this lecture, we are using the Neumann stability analysis, which only analyzes the stability of the discretization in the interior.